So I'll present Shard Scheduler. This is a joint work with Onur, Sergi, Alberto, Mustafa, and Etienne. I'm going to start with some basic definitions about blockchains and sharding. Then we'll define the problem of transactions in sharded environment. I'll then follow with the description of our system, Shard Scheduler, and I'll conclude with some performance evaluation. As you probably know at this point, blockchain is, well, a chain of blocks. Inside those blocks, we have some transactions. The blockchain is maintained by some miners. The miners receive transactions from the clients. They verify them, they order them, they pack them into the blocks, and then they attach the block on top of the chain. So with those transactions, the miners maintain some state. So we set the state of a set of objects. So we have an initial state based on the genesis block, and then every single transaction modifies the state. We have two main data models for blockchain. So either we have account-based. In account-based, we keep track of the balances of every single users, and UTXO. So in UTXO, we keep track of coins, who owns them, and whether they were spent or not. In this talk, we focus on the account-based blockchains. As we know from today's workshop, blockchains are great, but they have some severe performance limitations. We experience low throughput in terms of transactions per second, and also high user perceived latency. This is because of this requirement for a global consensus. So every single miner must agree on the same set of transactions, which means that now we have to disseminate the pending transactions and then blocks to all the miners. All the miners have to store those blocks plus the state of all the objects of the blockchain. And every single miner must validate every single transaction. So sharding is one of the techniques proposed as a solution to this problem. The main idea here is that we split the blockchain into groups called shards, and every single shard will have its own blocks, its own miners, transactions, and will hold a subset of the objects of the entire blockchain. And the hope here is that, well, if a single chain can support this specific amount of transactions, if we add more chains, then we can scale up the entire blockchain. Often this kind of sharded system, they have also what we call a beacon shard or the reference shard. So this is just a main shard that is used for coordination between shards. The beacon shard will usually store block headers of all the blocks being produced by every single shard, and also will be used to assign miners to the shards. So with the blockchain, we have these assumptions of the global honest majority. But in the sharded environment, we also must make sure that in every single shard, we have an honest majority as well. So this is usually done by creating some randomness on the beacon chain and then assigning, based on this randomness, miners to the shard in an unpredictable way. So this gives us this security guarantee. And the beacon shard will also shuffle or migrate the miners across shard over time to compensate for miners leaving and joining the network. So let's move to transactions in the sharded environment. As I said before, here we focus on the account-based model. So if I want to perform a single transaction, let's say a simple money transfer, let's say that Alice here wants to send money to Bob. In the account-based model, first of all, I have to deduct the balance of Alice by a specific amount. Then I have to increase the balance of Bob by the same amount, and I must make sure that this transaction is atomic, because I don't want either to create money out of thin air or destroy some money. Now, in the sharded environment, if Alice and Bob are in the same shard, this is easy. We create one transaction, we put it in the block in the specific shard, and it works. So this is exactly the same as in a single chain blockchain. But now if Alice wants to send a transaction to Charlie, who is in a different shard, the things get slightly more complicated, because now we need one transaction in shard 1 to deduct the balance of Alice. We now need another transaction in shard 2 to increase the balance of Charlie, and also we need some coordination between those blocks, between those shards, to make sure the whole operation is atomic. So by having a cross-shard transactions here, we more than double the cost of processing of this transaction. And the things get even more complicated when we add now smart contracts on top of that. So here, let's assume the simple procedure. You have a list of users to be paid. We have a fixed amount that we want to pay every single user. And in this function, we iterate through all the users. We check their balance. If they have less than 10 coins, we send them some money. Now, if all the users that we want to pay are in a single shard, this is easy. We create a single transaction with the contract invocation. We add it to the chain, and it's done. But now, if you assume that we have, let's say, 100 users being spread across multiple shards, then you need to create at least one transaction in every single shard. And also to make sure it's atomic, you need coordination with every single shard and all the miners from all those shards. So we increase the computational overhead quite extensively. So the bottom line here is that cross-shard transactions are costly, which means that the object placement is important, because now object to shard assignment can determine the performance of the entire sharded environment. And currently we use something that is called a hashed-based approach. This is a very simple thing. We just divide the hash space of the account IDs across shards. We hash the account ID, and then we can determine to which shard the specific account belongs. This is very simple. It is verifiable because everyone can just take an account ID, hash it, and verify if the account should belong to the specific shard. We can also expect good long-term load balance, because now if you randomly assign shards, accounts to shards, we can expect a more or less uniform load balance across the shards. However, we have problems with data locality. You can imagine that we'll have probably a lot of accounts that interact quite frequently, but are placed in different shards, creating a lot of costly cross-shard transactions. The other problem is no adaptation to short-term load spikes. Because this assignment is static, we cannot migrate accounts, so we cannot compensate for any load differences that we experience. So with this work, we ask the question whether we can migrate accounts across shards to improve the performance on the entire system, and also eliminate those problems that I mentioned before. And this brings me to Shard Scheduler. Shard Scheduler is a system that observes the interaction between accounts and load balance of every single shard, and based on that tries to create some migration recommendation. So saying this account should be migrated from this shard to this shard at this specific point of time. So to implement that, we first of all enhance the state of every single account by what we call an alignment vector. The alignment vector will basically tell you how many transactions with the specific shard an account had. So we have here Alice here, and we see that she had 3 transactions with shard 1, 1 transaction with shard 2, and 0 transactions with shard 3. Now, when Alice sends a transaction to Charlie in shard 2, we will increase her alignment towards shard 2 by 1, and also for Charlie, we'll increase his alignment towards shard 1 by 1 as well. On top of that, we also enhance the reference shard by gathering some statistic about load of every single shard. So we'll gather statistics in terms of the size of the transactions, like in Bitcoin, or the complexity or total gas usage as in Ethereum. So we know how loaded are all the shards. And using those data structures when Shard Scheduler encounters the cross-shard transactions, first of all, we try to determine the list of all the shards involved in the transactions. Once we have that, we look at the load balance statistics available from the reference shard, and we choose what we call a main shard for this transaction. So this will be the least loaded shard from across all the shards involved in this transaction. And now we go to every single account being modified by this transaction and not being in the main shard, and you ask the question whether this account should be migrated to this main shard. And to answer the question, we look at the alignment vector that we defined before. And the high-level idea here is that if we see a strong alignment of a user towards the shard it's currently allocated to, we don't want to migrate it because it can indicate that we have a strong community of highly interacting accounts already in this shard. On the other hand, if the alignment towards the current shard is weak in regards to the alignment to other shards, we are more likely to migrate the account to the main shard. So by using this simple technique, we can achieve the load balancing because now the main shard is the least loaded shard, so we move accounts towards this shard. We also preserve existing communities by using the alignment vector, and we also minimize the number of migrations because we only consider a migration during a cross-shard transactions, which means that we'll never consider migrating an inactive account. And we also introduce some migration thresholds to prevent accounts flip-flopping back and forth between shards. So now once we have those recommendations, we need a way to enforce them. And for many reasons that we list in the paper, we choose the miners to enforce those migrations based on the consensus. So the migration decisions or the recommendations are based on on-chain data, are fully verifiable, so we can just make them a part of the transaction processing. A transaction will not be considered as valid if it doesn't have the correct migrations of account across shards. So this gives us a lot of flexibility, but there's still one problem. So now if we consider again the same scenario, we have Alice paying Charlie. Alice is in shard 1, Charlie is in shard 2. And let's assume that the shard scheduler recommends moving Alice from shard 1 to shard 2. Now, if you're a miner in shard 1, you're not happy with the situation because your revenue depends on the transaction fee that are being paid in your shard. And by moving accounts away, you potentially lower your revenue. Even in a situation when shard 1 is fully overloaded and shard 2 and shard 3 are idle, as a miner in shard 1, you don't want to migrate any accounts out of your shards. So this is not great because even if you made the migrations a part of the consensus, the miners are incentivized to not follow the consensus because they can make more money by just keeping all the accounts for themselves. So to solve this problem, we introduced a new economic models for a sharded blockchain. And we use for that this miner rescheduling mechanisms that I introduced before. So you remember that the miners are assigned to the shards, but then periodically they will be reshuffled and assigned to a different shard by the reference chain. So now for every epoch, we calculate the total amount of fees gathered in every shard. So here in shard 1, in epoch 1, we see that this shard collected 100 coins in the total fees. Then for each miner, we calculate the participation. So what percentage of this entire amount each miner collected. So our miner here collected 20% of this 100 coins. At this point, the miners will not get this money, but we wait for the next epoch for the reassignment. So this now in this next epoch, our miner will be reassigned to shard 2. And at this point, it will cash 20%, so it's participation, but not of this 100, but of 50, which is the amount gathered in this new shard, but in the previous epoch. So now the miners are still incentivized to maximize their participation, so to mine as many blocks as they can. But also we prove in the paper that now they're incentivized to care about the global throughput of the entire blockchain rather than focusing on their own shard. And this is because they don't know in which shard they were going to be assigned, so they don't know from which pot they're going to take their money. So I'm going to finish with some performance evaluation. We implemented Shard Scheduler at the beginning as a Python simulator. We compared it against the hash-based solution that I discussed before, and also against the Metis. So Metis is a graph partition algorithm. So what we did, we took all the transactions in Ethereum, we fed them to Metis, creating a graph of interaction between accounts. And then we told Metis to try to split them into groups so that we don't have a lot of cross-shard transactions, but also keep some load balance across the shards. But you can see that even then, especially for a high number of shards, a shard scheduler achieves much higher throughput. And this is because we can perform the migrations on the fly when they are needed and compensate for any load inequalities or react to some new communities being formed or old communities being disbanded. Both those approaches, even if Metis knows all the transactions in the future, they cannot adapt to some rapid changes in the network dynamics. With the higher throughput, we also experience lower average latency. In our experiments, we achieve up to 70% reduction in user perceived latency. And the general rule of thumb is that the more shards we add, the more effective shard scheduler becomes. We then implemented shard scheduler on top of Chainspace. Chainspace is a sharded blockchain with the support of smart contracts. We then implemented it on top of the Chainspace miners. We put them on Amazon AWS for different configurations and different number of miners. And again, we experienced a high increase in the throughput, as well as a significant decrease in the user perceived latency. So to conclude, we have a migration recommendation system that is fully deterministic, is based uniquely on on-chain data, and can be made part of the consensus protocol. It's also very lightweight because we use also simple mathematical operations. So it does not introduce a lot of overhead on top of transaction verification mechanism. We also built an economic system that binds the rewards received by the miners to the throughput of the entire blockchain and not to a specific shard. So it basically incentivizes the honest nodes to follow the protocol and to remain honest, because that's the strategy that will give them the most payoff. And finally, in terms of performance, we observe up to 3-fold throughput increase and up to 70% user perceived latency reduction. Our data set with all the transactions from Ethereum, also the internal transactions from the smart contracts, and the accounts being modified by every single transaction is available under this link. Feel free to contact us if you want to play more with the code and you experience any issues. And I think this is it from me. Thank you.
Thanks a lot, Michael. Any questions from the audience? Otherwise, I can start while questions are trickling in. So, I mean, thanks a lot for your extensive background on shards in general. I think this was quite helpful. But what basically came to my mind is, how do you compare cross-shard transactions with cross-blockchain transactions? Or more specifically, how is the design space of cross-chain bridges different from cross-shard transaction mechanisms?
Right, so I'm not an expert in cross-blockchain communication, so to be honest, it's pretty difficult for me to compare. I would say that cross-shard are kind of easier because you have at least the same data model, you have at least the same consensus protocol. So I'd say it's easier. So I think once you make an efficient cross-shard transactions, then you can move to cross-blockchain transactions. But yeah, this is a good question. I'm not entirely sure what differences we might see here. Right. I mean, so sorry, yeah.
No, go ahead. Yep.
I mean, in our design, also what we, in cross-shard transactions, there is this famous problem of train and hotel. When you want to reserve the train only if the hotel goes through, you also need, first of all, there are difficult questions when, first of all, you need to determine all the accounts being involved in the transaction. Then you need to determine all the shards being determined in the transactions. And this is very difficult even within one blockchain that is sharded, because you have to query some external shards. So you need to be a client, at least a light client for other shards. This makes things even more complicated if you do the cross-blockchain interactions, because it's difficult to be a client of a different blockchain. So I think the cross-blockchain transactions will be also much more limited than the cross-shard transactions.
Okay. Then another question I had is I noticed you have an entity or somebody has to be identifying the main shard, if I'm not mistaken, right? So is this kind of an additional centralized trusted entity that's doing this? So what if I attack this entity? What could I maliciously kind of change?
No, so this main shard, this is envisioned by systems such as RapidChain or even in Ethereum. So this is just this main shard. So usually you have some miners as a committee on this main shard, and then they just generate some randomness, and based on this randomness, you assign other miners to different shards. So this is just like that's a regular shard, but it has a different purpose. So it doesn't create any data or validate transactions, but the transaction will be just for blockchain management, let's say.
Because I thought I understood that the main shard was the one that's the most active one, and then you somehow need to identify it, right? Or according to some metrics, or is this elected by the committee as you just suggested?
So the miners will be elected by some committee, so it depends on the blockchain. But this main chain is just a regular blockchain, let's say, and so it acts again as a regular. It's not a centralized entity; is just a blockchain on its own. But its entire purpose is just to kind of deal with the logistics of the sharded blockchain.
Okay, excellent. So Jeremy actually just asked a question in the Q&A. I'm afraid we have to jump on the next talk already, but please feel free to answer the question in the chat. I will also add a few more that I had. And yeah, everyone feel free to just add your questions in the Q&A. So thanks a lot, Michał.
Perfect, thank you.